15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on this, the 233rd edition of the Space Nuts podcast. My name is Andrew Dunkley, and with me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Ta-da! Yes, here I am, and I can see the trace of my voice going, so I know I'm here. Thank you, Andrew.
Yes. Now, yes, and I should mention that there will not be a video edition this week due to technical difficulties. I'll use the standard industry phraseology to cover us on that one. In short, we couldn't connect on the interface with the video recorder, and so we had to drop it. Not for want of trying, though, Fred, I must say.
We certainly tried.
Yeah, we did.
Never mind. That's all right.
That's all right. We've gone back to old reliable, and it is called analog tape. No, we didn't go back that far, but. Here we are. Now, how you been, Fred? By the way, it's really, really busy this time of year. In my other role as an employee of the Salvation Army, it's the busiest time of year for us because we're trying to get all sorts of things together to help people out so that they can have a Christmas. We distributed over 100. Hampers and boxes of toys last week to people who wouldn't have had anything this Christmas, so that was good. And this year's been amazing because with COVID-19 you'd think it would slow everything down because we can't do things that we'd normally do to collect toys and money, and people have just come out of the woodwork to help. It's just been fantastic. It's just a wonderful thing to see that people are actually going out of their way to assist with people in need. So we've been able to do quite a bit this year that we didn't think we'd get done. So it's been all hands on deck, but we've been able to help at least 100 families, which is terrific.
Sounds good.
So yes, it does. Now we have got a fair bit to cover today. We're also going to be adding some Patreon material, some bonus material for our patrons. We'll tell you about that later. But on this edition, we're going to talk about the Great Conjunction, which happens every so often. But this particular conjunction, hasn't been seen for many a long time, and we're talking hundreds of years. It also looks like there's some kind of link between radio bursts and the flares of cool stars. We call those stars Fonzie stars. And we've got some questions to answer from Alex in Bellingen about neutron stars. Zoe wants to know about Santa and the time dilation advantages that he enjoys. And Travis is still trying to get his head around black holes, why they have differing mass, because they're a singularity. How could it be? That is a good question. I think we've been there before, but it's worth reinvestigating. So we're going to do all of that today on this edition of Space Nuts. But first, Fred, let's talk about the Great Conjunction. They're calling it the Great Conjunction, and it will be great, as far as I can tell.
Indeed, yeah. So a Great Conjunction is defined as being a conjunction of the two great planets, Jupiter and Saturn. And typically there's one of those every 20 years where they come together in the sky. Of course, they're not coming together in reality because Saturn's, well over 1.5 times further away in the solar system than Jupiter is, but they appear to come together in the sky. So that is the kind of definition of a conjunction, but it turns out that this one is an exceptionally unusual one because they will be 1/10 of a degree apart, and that is almost on the limit where, unless your eyes are pretty good, you might see them as just one bright star. Depends on your eyesight. Now, the last time this happened, Andrew, was on the 16th of July, 1623, which I don't remember directly, but it was in the early history of the telescope. The telescope appeared in the historical record in 1608. However, there is an issue with that because that particular conjunction probably nobody saw because they were very close to the sun. So they would not really be obvious in the night sky, too close to the sun. And so in order to see one that would, or to recognize one that would have been seen by most people, you've got to go back a bit further to the 4th of March, 1226. So almost 800 years ago, they would have been seen together in the sky at this sort of distance, about a tenth of a degree. So a tenth of a degree is a fifth of the diameter of the moon. That just puts it in perspective. And it happens by curious coincidence on the solstice, the summer solstice for us, the winter solstice for the folk in the Northern Hemisphere, the 21st of December. So it's really quite a phenomenal astronomical event. And if you happen to be listening to this podcast after the 21st of December, you've missed it. Actually, that's not quite. It's not quite true, because the planets don't whiz through the sky at breakneck speed. They're actually relatively sedate in their movement through the sky. And so even now, Jupiter and Saturn, what are we, not quite a week ahead of this, Jupiter and Saturn are very close. And it'll be the same for a week afterwards. They'll be noticeably closer than they normally are. Jupiter, of course, the brighter one, Saturn, the fainter one. If people are listening to this, though, before the 17th of December, then it's worth a look, because the crescent moon will be very nearby in the evening sky. You'll see the crescent moon and the two close planets, which should look lovely. The problem we've got here in coastal New South Wales is that we've got solid cloud. And I'm not even sure that we're going to see the conjunction itself next week, because the forecast is so bad. But I'm sure people who can, get a good view of the sky, they should go out after sunset, wait for the sky to get dark, and you will see the two planets in the western evening sky.
Will it be something that people will be able to photograph? Because I've already seen a lot of photographs on social media. People have been getting some snapshots of the planets already, and obviously some people have got some good gear to be able to do that. But do you need a telescope or binoculars or something like that? Yeah,
it would help if you've got probably a pair of binoculars that you could stick your smartphone on the back of. But some people have just been using ordinary smartphones and getting really quite nice pictures. The two planets don't show up very, very brightly. What's a really interesting possibility, because they're so close on the 21st, anybody who's set up with a small telescope and the wherewithal to photograph things should be able to get both the planets in the same field of view. So you'll see both Saturn and Jupiter, along with their brighter moons, probably Titan and Europa, Io, Ganymede, and Callisto, the moons of Jupiter. So I think we will see some really spectacular photos next week coming from people who've got a small telescope.
Now, is there anything scientific we can learn from this? Is there interest in the professional world when it comes to space science, or is this just a pretty thing to see?
It is. That's more or less what it is. What's great about it, of course, is that it lets folk like us talk about this sort of thing, and that in the broader media, people will certainly be switched on to the fact that there's something interesting happening in the sky, and that always draws attention to astronomy and space science. It kind of reminds people that we live in this giant clockwork system called the solar system, and it does interesting things. So not really any science to come from it, but some, I hope, very nice images and perhaps a lot of news coverage as well.
Oh, there'll be plenty of news coverage. You know what amuses me, Fred, though, is that we get so excited about the Great Conjunction, which is only an optical illusion because of our perspective.
It is, that's right.
But in reality, we're just looking at two planets that have been there all the time, and they're not even close to each other. It's just the way we're perceiving it at this particular time.
That's right.
And yet the world's going a bit crazy about it. It's it's interesting.
But that's the point. That it's great when there is something in the sky that people want to go crazy about. We'll go with the flow, Andrew.
Yes, indeed. I suppose the other thing that's interesting is we can predict these things so well now. We know when and where and how these things are all going to happen. It's all very well documented and calculated. And I suppose if you wanted to, you could sit down and give the date of the exact next one.
Yep,
Because
2060.
Sorry?
2060.
There you are.
Let me give you a date for it. April the 7th. Actually, the next one's November 2nd, 2040, and there's one April the 7th, 2060. But these are actually, they're just bog standard great conjunctions. They're nowhere near as close as this one.
Oh, they're just ordinary
great conjunctions, that's right.
I do recall one, it's going back a few years now, where just about every planet lined up, wasn't it?
Yeah, that's right.
I remember when.
It was a few years ago. The next one of those, if I remember rightly, will be in 2040, September 2040. I wrote about it in one of my books a while ago.
Okay.
And that's all 5 naked eye planets.
I'm just thinking with the technology that will be available then, imagine the pictures, because for every 10, 20 years that passes, the technology has leapt, miles ahead.
Yeah.
And who knows what they're going to be able to photograph in 20 years' time.
It'll be good. It'll be good.
Yeah. It'll be ET giving us the bird. That's what it will be.
Maybe so.
All right. Well, that's the 21st of December. If you've got clear skies, grab your smart device or your optical zoom digital camera. Mine's got 40 times optical zoom. Do you think that'll help?
It certainly will. Yep.
Oh, good. I'll have a crack. If it's not cloudy, we've got some cloudy weather predicted as well, so we might not see anything, but we'll give it a try. That's the 21st of December, the Great Conjunction. You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
This is the Space Nuts podcast with Andrew Dunkley and Fred Watson. I want to shout out to a couple of patrons. These are people who have put their money where our podcast is, and we really appreciate that. Daryl in South Australia and Michael in San Francisco. Thank you so much for your wonderful support of our podcast. You don't know how much it means to us. We just appreciate it so much, and it certainly is a nice gesture. And here's something to think about. I often suggest to you that you might like to become a patron, and we've got all these package deals and all these subscription options available through Patreon and Supercast. But have you thought about buying a 12-month subscription as a Christmas present? Maybe you've got someone who is difficult to buy for, and there are lots of people in that category. Perhaps you can offer them a subscription to Patreon or Supercast and give them 12 months of Space Nuts. If you would like to do that, go to patreon.com/spacenuts or to our Supercast page. All the details are on our website, but it's worth a thought, and it's not overly expensive, is it? Patreon.com/spacenuts or go to spacenutspodcast.com for all the details. But something to think about. Now, Fred, moving on from the Great Conjunction to fast radio bursts and the flares around cool Fonzie stars.
Yeah, these are not fast radio bursts. These are ordinary radio bursts.
Radio bursts.
Yeah, that's right.
Average radio bursts.
Yeah, fast radio bursts are very specific. They're of order of milliseconds and very, very bright, and we still only have a vague idea of what causes them. Probably flares on magnetars. There you are, which are magnetized neutron stars. Never mind, that's not what we're talking about. What we are talking about, though, here is something that I think astronomers have suspected for a long time, and it relates to the commonest form of stars that there are in our galaxy, and that is something called M-dwarf stars, which you can think of as things significantly smaller and cooler than our sun, which of course radiate less intense radiation because they're not as big, so they're not shining as brightly. The key thing here is that they make up something like 70% of all the stars in our galaxy. So they are really, really prolific. And in fact, the nearest star to us, Proxima Centauri, which is part of the Alpha Centauri system, 4.2 light years away, that is an M dwarf. It's one of these stars which are the commonest in the galaxy. So people have suspected that whilst we've detected many planets around M dwarfs, because they're actually easier to find around an M dwarf because this parent star is not, blinding you with its own brilliance. Even though we know lots of planets around M dwarf stars, they might be not in a good place because it has been known for a long time that M dwarf stars have quite bright flares, stellar flares, which send copious quantities of subatomic radiation out into their vicinity. And that's, the suspicion has been this might be bad for any kind of life forms evolving on a planet around one of these M dwarf stars. And that's a good point, which in a sense has now been confirmed. Because what has happened is that astronomers, and some of them are based here in Australia, they have detected that sort of radio burst signature, which you measure with a radio telescope, actually is telling you about flares. These things the radio bursts are something you can monitor. And what it's doing is telling you literally about the space weather around one of these stars, or actually any star in the solar system, outside the solar system, any star in our galaxy, but which most commonly are M dwarf stars. So we've got the wherewithal to measure their radiation, which we didn't have before. That is the good news. The bad news is, it's not so good. There are lots of them, very intense blasts of plasma coming from these stars, which might well be a very bad thing for any life forms on planets around them. And the research on this, which, by the way, does have a strong Australian content, CSIRO, the University of Western Australia, Curtin University, they're all in Australia, and University of Colorado, and University of Wisconsin, Milwaukee, which is not in Australia.
No.
And also, I think
it's where the cheeseheads live.
I'm not going to make any comment on that. Just to move on to say that there's also a contribution from the University of California, Berkeley. There you go.
I wasn't being rude. It's a term of endearment if you're a cheesehead.
Is it? Oh,
yeah.
It's not one of those football things, is it?
Yeah, it is.
There's nothing endearing about football, Andrew.
Fair enough.
So a multinational collaboration, which has detected, the fact that, yes, we're right, we might have problems with any kind of life forms trying to evolve on a planet of a red dwarf. And in fact, the research points specifically to the two known Earth-sized planets, or two suspected Earth-sized planets, which are orbiting Proxima Centauri. They're maybe not Earth-sized, perhaps Earth-like is better because they're thought to be rocky planets. And they're thought to be within the habitable zone of Proxima Centauri, which is where you can get liquid water, as you know. So that's great. You've got all that, but then you've got these horrendous solar flares being slung at you periodically from the parent star, and that's why this is not really a good news story in the quest for life beyond the solar system.
Although the positive being that if these dwarf M-class stars exist in such massive numbers, but the proximity of the planet to the star to be in the habitable zone puts it too close because of solar flare activity, then we only have to look at 30% of the stars to find life, really.
Yes, that's right, which are harder to detect. Or the planets of them are harder to detect. Although these days, with the TESS spacecraft, the former Kepler spacecraft, and the role of amateur astronomers now, who have got, sufficiently precise equipment with their telescopes that they can measure this tiny dip in the brightness of a star caused by a planet going past. So we've got a lot to go by. So yes, I take your point. The other 30% are probably the place to look if you want to look for living organisms.
Yeah, these dwarf M-class stars sound like they are probably not somewhere you'd like to be orbiting.
Yes.
in terms of planetary habitation. I mean, our star does the same thing, but we are far enough away for it not to be a massive issue. Although from time to time, we do have problems with solar flares and coronal mass ejections, and the big worry is that now that we are living in a digital world and rely so much, almost 100% on electronics around the globe now, we could get an electromagnetic pulse of such significance that we could find ourselves in very big trouble in a very short period of time.
Indeed, that's right. In particular, one, the Carrington event, which was, in 1859, I think, if I remember rightly, which fried all the primitive electronic communications.
Telegraph.
Yes, that's right, the telegraph. Something like that would certainly upset both our power supplies here on Earth, because it trips out it overloads the transformers and trips out their fail-safe mechanisms. But also, as you say, the digital era, especially with spacecraft up there above the atmosphere, they're feeling the full brunt of this. Fortunately, our sun does not chuck out as horrendous solar flares as dwarf stars do, but it's still bad enough. You can get them from time to time, and your warning is well taken.
Would we get a warning though if something like that were building up? Is there any way of telling that it might be happening?
Yes, so that's one reason why we've got such a flotilla of satellites in orbit around the sun at the moment, monitoring all these things. And there's a new solar telescope, a 4-meter telescope dedicated to looking at the sun, which is on the mountain Haleakala on Maui, in the Hawaiian Islands. That is also interested in understanding the way it's all about magnetic fields in sunspots and things of that sort, the way these magnetic fields kind of build up and then twang, and in doing that, they, as they release themselves from the surface, they spread these high energy particles throughout space. So you can get some warning. And I think as time goes on, we'll be better equipped to do that, which is just as well, given what you've just said, that we are very vulnerable with the electronics that we use today.
We should just sort of sheet everything in lead and be done with it.
Yes, that's right.
Would that work?
Look, I like the steampunk solutions, and lead's one of them. There's no doubt about that.
There you are. Okay. Yeah, it's good stuff, lead.
Oh, yeah.
I used to chew it off my cradle when I was a kid. Yeah. Yeah. All right. So if you're thinking of moving because of COVID-19, dwarf M-class stars are probably not a good option. Just keep that in mind. You're listening to Space Nuts, the podcast all about space, science and astronomy and stuff. You're with Andrew Dunkley and, of course, Fred Watson.
3, 2, 1.
Space Nuts.
Thanks for listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson. Now, Fred, before we get to the audio question and the 2 text questions we've received, we're doing 3 questions today. Holy mother, how are we going to handle that? I just want to send a shout out to all our social media supporters, whether it's Twitter or Facebook or Instagram or what's another one? Pinterest. We're on Pinterest. All sorts of places where you can find us. And, of course, YouTube, where our numbers continue to grow. And we're getting a lot more feedback from the YouTube audience, regular questions and comments these days, which is fantastic. So, thank you all for not only following the podcast directly, but for supporting us on our various social media platforms. And, of course, one of my favourite groups is the Space Nuts podcast podcast group, which is a group that was created by Space Nuts listeners so that they could all talk to each other and swap ideas and answer each other's questions. It is fantastic. One of the things that seems to be getting a bit of momentum on the page, Fred, is this mysterious monolith that keeps popping up all over the world. Have you heard that story?
Yes.
Yeah. It sort of it turns up somewhere mysteriously, then it disappears, and then it comes up somewhere else. And now we've got people putting monoliths all over the world, copycats. I think that's great stuff. I like that kind of thing. And it's somewhat meaningless, but it makes people smile, and that can only be a good thing. So thanks to all our social media supporters. Now, Fred, we've got a question, and this one comes from Alex in Bellingen in northern New South Wales.
Hi Andrew, this is Alex from Bellingen, New South Wales, a very, very wet Bellingen. I have a question for you and Professor Watson about neutron stars. We often read or hear statements like, a teaspoon of neutron star would weigh 1 billion tonnes on Earth. The actual weight quoted seems to vary, depending on the source you read, and I guess whether we're talking about a cooking measure or one of those souvenir teaspoons. Still, the main idea being to get across just how incredibly dense such objects are. But weight and mass are not the same thing, mass being an intrinsic property of matter, while weight is a measure of force and depends on the gravitational field. For example, we'd all weigh less on the Moon, despite having the same mass. So I was wondering, how much would a teaspoon of neutron star weigh on the surface of a neutron star? Thanks to you both for the podcast. Very much enjoy listening.
Thank you, Alex, and good luck with everything up on the North Coast. I've seen some of the pictures of the devastation up there from the tidal surges and the beach erosion and the flooding. And I think there was one place yesterday recorded 952 millimetres of rain in a day, which is just an extraordinary amount of rain. I don't know what that is in the old scale in inches, but it's a massive, massive number. So, our thoughts are with you and everybody on the North Coast, Alex. It's usually a quite beautiful place and very, very popular around holiday time. But at the moment, it's a little bit of a mess with all that rain and flooding. So fingers crossed it'll clear away very quickly. Now, he brings up an interesting point. The weight of a teaspoon of a neutron star on a neutron star compared, I guess, with what it would weigh here, Fred.
Yeah, that's right. So Alex's point is well made. We throw around the terms weight and mass rather indiscriminately, but they are different. The mass is the intrinsic amount in something, and the weight is what it would weigh when it's in a gravitational field. So he's quite right to separate them. And the answer's, I think, pretty interesting. Look, Alex also mentioned that the density of neutron stars seems to be a movable feast as well. But I'm reading from a reputable website, which is involved with nuclear power and things of that sort. And the suggestion here is that a neutron star, well, if you got the teaspoonful of its material, which is the normal quantity, 1 teaspoonful has a mass of 5.5 times 10 to the 12 kilograms. So that's 5.5 trillion kilograms.
Good grief.
That's a lot. Yeah, that's its mass.
Yeah.
Neutron stars are the most dense things you can have, because anything more dense will become a black hole. It collapses under its own mass. So 5.5 trillion kilograms. But now you take your teaspoon and you weigh it on the surface of the neutron star, because that's now the weight that you're talking about and not the mass. And what it does is it goes up by another 10 to the 11 times.
So I thought you were going to say, and it weighs 5 grams.
No,
something. It's the opposite.
It weighs that number. Well, compared with the Earth, let me put it that way. Compared with the Earth, it's 10 to the 11 times more.
Gosh.
So, and this is, calculations of typical neutron stars' surface gravity, because neutron stars they've got all this mass in them, about the same as a star, and yet they're only 10 kilometers across. So they've got this huge density. And you're right next to it if you're on the surface. The acceleration due to gravity on the Earth is 9.9 meters per second squared. 9.9, nearly 10. Or 9.8, I think it is actually 9.8. So that's what our gravitational acceleration is. If you drop something on the surface of the Earth, that's the speed at which it accelerates, 9.8. Every second, speed increases by 9.8 meters per second. On a neutron star, you drop it, and every second its speed increases by 7 times 10 to the 12 meters per second. In other words, 7 trillion meters per second. Yeah, they go very fast, but not very far because the neutron star is so small. So Alex's point is well made. The weight of a teaspoonful of matter on the surface of a neutron star is just humongous. It's very, very large.
I suppose also if you dropped something on a neutron star with that kind of acceleration, it would make several sonic booms before it hit the surface.
Maybe. Yes, maybe. If there's
and blow you to smithereens in the process.
You'd be squashed flat already because of that gravitational field is crippling. It's your head is significantly feeling more pressure downwards than your feet are, so there's not much left of you. It's not a good place to be. A great question.
So no M-class dwarf star occupation and neutron stars are out. We're running out of places to move.
We are, yes, indeed.
Yes. All right. Appreciate the question. Thank you, Alex. And again, good luck with everything up on the North Coast. Let's move on to our next question. This comes from Zoe Whiteside. Hey, Zoe here again. I think I clicked onto something this week. As Santa delivers every child a present in one night, that would indicate that he can travel at the speed of light, on which would explain why he lives so long. Does this give definitive proof of Einstein's special relativity? My realistic question, however, is, does the influence of gravity extend out forever? Cheers, love the podcast, keep it up. Look, I've heard the Santa argument many, many times.
Yes.
She's put an interesting angle on it, though. I think that's really good.
About him living forever, that's right.
Yeah,
so long. I have seen that. I haven't had time to dig this out, but there's a paper that crops up every so often about the fact, if Santa Claus can deliver a present to everywhere on the Earth in one night, what is his speed? And it certainly is relativistic. It's not necessarily at the speed of light, but getting there. So the speed of light, if I remember rightly, I know, once again, should be able to do the calculation in my head, but I can't. Yes, I can, probably. It's about right. The light, if you could make it go around the Earth, it would go around 7 times in 1 second. So that's the speed of light. So if he can travel at that speed, he probably could. He could just nip about all over the place. Although, you've got to be at a place where the chimneys are open and it's dark, so nobody can see everybody. So you've got to do it one hemisphere at a time. And being able to travel at the speed of light is interesting because you don't, as exactly as she says, photons do not experience time. They're the only things that can travel at the speed of light, but they don't experience time. And so Santa Claus wouldn't either. So that's why he's been around for so long. Now, turning to the other question, does the influence of gravity extend out forever? And the answer is yes, it does. But it gets very small as you get further away from it. In fact, gravity obeys what's called the inverse square law. So for every kilometre that you move away from something with gravitation, its influence drops by 1 kilometre squared. For every 2 kilometres, it's 4 kilometres. It drops off as a square of the distance. But it's one of these forces that doesn't seem to have a distance limit. It just gets very, very weak. Gravity is the one force that we understand least, and that, I guess, is really, we might discover, if we find that gravity is quantized, if there's a quantum theory of gravity, we might discover that there is a minimum amount of gravity that you can have, and that would then suggest that actually there is a limit to how far gravity extends. But at the moment, we don't know that, and we think it just goes on forever.
What would we be able to do if we could crack it? If we could understand gravity, know what it is, how it works, everything about it, what difference would it make to us?
Well, if we could do that, and maybe we could do some clever engineering that would let us manipulate gravity, and then you're in really interesting territory. If you can manipulate gravity, you can forget about launching spaceships. You just build your anti-gravity device and off it goes. So that would be something that might happen.
Yeah, well, that issue was very well portrayed in the movie Interstellar, where they had to rescue the human race from a dying planet, and two elements to the story: finding somewhere new to live, but getting them off Earth in the meantime, and having them live on a space station that you couldn't launch into space. You had to solve the problem of gravity to get off the Earth.
Yes,
and voila. That's what that story was about. I love that movie. I really do. But that kind of was the problem. So we've still got a heck of a lot to learn, haven't we?
We do. I'm going to give a taster here, which I don't normally do. As you know, I'm working on my very first children's book, and I'm also illustrating it as well as writing the text. And when it comes out next year, you will find in it there is a diagram. It's actually a cartoon, but it shows you how to build an anti-gravity device. It's right there in front of you.
You're going to have lots and lots of students doing this at school and sending you their pictures. Yeah, I reckon.
Maybe so.
I think that's a great idea. Yeah. All right. Thank you, Zoe. Great question. Good discussion, and I'm sure in the years to come we will get the paper on Santa Claus's speed over and over again. Let's move on to a question from Travis Bell. Hi, Travis. Hey, guys. Loved the show. How can a black hole have different amounts of mass if the singularity has infinite density? Can't get my head around this. Travis, can anyone get their head around it?
Yes. Well, mathematically you can, because it's a very easy... the answer is straightforward.
There's the stumbling block straight up for me.
Oh, no, you'll get this. Okay, so everything that Travis says is right. Black holes have different amounts of mass. They have infinite density. That's actually the definition of a black hole. It is a point in space of infinite density. And he also mentions a singularity, which is what this is. It's a single point in space with infinite density. Okay, so density is mass over volume. That's the mathematics. Now, if you think about that little equation, density has got to be infinite. And the reason why it's infinite is because the volume on the bottom line is zero. It is a point of no dimensions. So the volume of your black hole is zero. And that means it doesn't matter what the mass is. You can put any mass you like on the top line of the equation. You're still going to get an infinite density because the volume's zero. So that's why you can have... Did you get that?
Yeah.
Hey! Yeah, that's why you can have you can have different masses of black holes, and you can measure the different mass, by a number of methods, usually involving how fast things are going around the black hole. but the volume is always zero, and because that's what defines a black hole.
I've come a long way since year 7, which is for those in America, junior high. I've come a long way since my 3 times 0 equals 3 answer, my first test in the maths class. Gee, I got tricked. There's a trick question, and just about everyone falls for that one. Yeah. Well, you didn't probably, Fred, but I did. Because I don't concentrate. My problem is I just don't think. I don't pre-read the questions. I just go, oh, that's close enough.
Yeah, yes. She'll be right.
All right.
Yep.
That's the attitude.
Yes.
And it never was, It never was in maths. No. It was never right. Oh dear. All right, Travis, thanks so much for your question. Appreciate it. Thanks to everybody who contributed this week. And if you do want to send in questions, you can do that via our website, spacenutspodcast.com. You can either send them through the email interface as a text, or you can record them via the AMA tab and check out the Space Nuts shop while you're there, and maybe pick up a nice prezi for Christmas for yourself or someone else, or for every person on the planet. That'd be really good if you could do that. But maybe just, one mug at a time. Not talking about us, Fred. Well, maybe we are. But anyway, thanks for your support. And we will be back next week, Fred. I think we're going to do a Christmas edition. Why not?
It sounds good. Christmas edition, we can report on the conjunction, whether anybody actually saw it through the clouds, and and do a few questions as while we're at it. How's that?
Well, if there are clear skies here, I'll do my level best to get a photo of it.
Yeah, that would be good.
But we'll see how it goes. Thanks, Fred. Always good to talk. We'll catch you next time.
Sounds great. See you soon.
Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast. And from me, Andrew Dunkley, thanks again. We'll talk to you again real soon.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.